On the morning of March 21, 1986, a man named Voyne Cox walked into an oncology clinic in Tyler, Texas, for his 9th cancer treatment. He had been treated by this machine 8 times already. It was a standard radiation therapy device, used in hundreds of hospitals around the world. The procedure took about a minute. It was supposed to be routine. When the operator pressed the button to begin treatment, Voyne Cox heard a frying sound. He felt his back catch fire. He stood up and walked out of the room, asking what had just happened to him. Nobody, including the operator, knew the answer for 3 more weeks. And by the time anyone figured it out, the same machine, in the same configuration, was already doing the same thing to other people. The machine was called the therac 25. It was manufactured by a Canadian government agency called Atomic Energy of Canada Limited, in partnership with a French company called CGR. It was, at the time, considered one of the most advanced medical devices in the world. It worked by firing a beam of accelerated electrons at the patient's tumor. The beam could be configured in 2 modes. In low-power electron mode, the beam went directly into the patient and burned a precisely targeted volume of cancer cells. In high-power X-ray mode, the beam was first aimed at a thick metal plate that converted the electrons into X-rays, which then penetrated deeper into the body to reach tumors near bone or organs. The difference between these 2 modes was enormous. In electron mode, the machine delivered a few hundred rads of radiation, calibrated precisely to the tumor. In X-ray mode, before the metal plate did its work, the raw electron beam coming out of the accelerator was roughly 100 times more powerful. The metal plate spread it out, slowed it down, and turned it into a safe medical dose. Without the metal plate, the raw electron beam would be a focused industrial death ray. Hospitals using the machine were aware of this, in a vague sense. They trusted the machine to never let that happen. The therac 25 had 2 safeguards to ensure it never did. The first was a physical interlock. The metal plate had to be in position before the high-power beam could be activated. The second was a software check. The machine's computer was supposed to verify that the operator's settings matched the physical configuration of the machine before any beam was fired. Both safeguards, on paper, looked solid. The earlier therac 20 model, used safely for years, had a backup hardware interlock that physically blocked the beam if the plate was missing. The therac 25 had removed that hardware interlock. The engineers had decided the software was reliable enough to handle it alone. To understand what happened, you have to know one technical thing about how the therac 25 was operated. The operator sat in a separate room from the patient, at a terminal that looked like an early DOS prompt. They would type in the patient's information, the treatment mode, the dose, and the duration. Then they would press a key labeled B for beam. The therac 25 was an old design that had been ported, several years earlier, to a new computer system. The new system supported faster typing. The old version of the code, designed for slower hardware, made an assumption that no one had questioned. It assumed that if the operator changed a setting after entering it, the machine had enough time to physically reconfigure itself before the next command arrived. In the slow original system, that was true. The operator simply could not type fast enough to outrun the machine. In the new system, an experienced operator who knew the keyboard could. If an operator entered the high-power X-ray setting, then within about 8 seconds noticed they had made a mistake, hit the up arrow, changed it to low-power electron mode, and pressed beam, the software registered the change. It thought the machine was in electron mode, but the physical machine had not finished moving the metal plate yet. The plate was still out of position from the previous setting. The software had updated. The hardware had not. The machine fired. In electron mode, with no metal plate, the patient received the raw high-power beam directly into their body. Around 100 times the intended dose. Concentrated into a small area, in a single second. Engineers later estimated the dose at between 15,000 and 25,000 rads. A normal therapeutic dose is about 200. Most people who receive a dose that high are dead within months. Some are dead within hours. This particular bug is what computer scientists call a race condition. 2 parts of a system, operating at different speeds, can end up in a state that neither one anticipated. The bug had existed in the therac 25 code for years. It had been triggered at least 3 times before Tyler, in different cities, with different patients. Each time, the symptoms were attributed to something else. Equipment malfunction, operator error. The patient being hypersensitive to radiation. None of the previous incidents had been formally reported to the manufacturer. None had been investigated. Most of the patients had died, and the cause of death had been recorded as the cancer the treatment was supposed to cure. Voyne Cox was the first patient who walked out of the room and said out loud, that something had gone wrong. After Voight Cox was injured, the operator and the medical physicist at the Tyler Clinic spent days trying to reproduce the problem. They could not. The machine, when they tested it under normal conditions, worked correctly. Then, on April 11th, 3 weeks later, a different patient at the same clinic, an older man named Verdun Kidd, walked into the same room for a routine treatment of skin cancer on his ear. The same thing happened. The same fast operator, the same correction sequence, the same fatal exposure. Verdun Kidd died within 3 weeks. He became, as far as anyone can tell, the first person ever recorded as having been killed by a software bug. This time, the medical physicist at the clinic, a man named Fritz Hager, refused to let it go. He sat at the operator's terminal for hours, day after day, typing different sequences as fast as he could, until he was able to make the machine misbehave in exactly the same way. Once he could reproduce the failure on demand, he did something nobody else had managed to do. He proved that it was the software. Hager called the manufacturer. The manufacturer's initial response was that the machine had no such defect, and that the issue must be operator error or hardware sabotage. Hager kept calling. Eventually, the Canadian Regulatory Authority got involved. The machine was taken out of service across North America in mid-1987. By that point, 4 more patients had been injured. At least 3 of them had died. The total death toll attributed to the therac 25 bug, by the time the investigation concluded, was at least 3 confirmed, and likely 6. The injuries to surviving patients were severe. Several lost limbs to radiation burns. 1 was paralyzed. The manufacturer issued a software fix. The new version added back the hardware interlock that the original design had removed. The lesson, as written into the official accident report, was painfully simple. Software is not, by itself, a substitute for a hardware safety system. No matter how confident the engineers are in their code, a physical machine handling lethal energy needs a physical safeguard. The software can fail. The hardware should not be able to fail with it. The therac 25 case is now taught in nearly every undergraduate software engineering program in the world. It is the foundational example in the field called software safety engineering, the discipline that asks what happens when code is the thing keeping people alive. From this single case, an entire methodology was built. Modern safety-critical software, the kind used in aviation, medical devices, automotive systems, and industrial automation, is now written under formal review processes that did not exist in 1985. Every assumption in the code is documented. Every safety property is independently verified. Hardware interlocks are mandatory by law. Race conditions are treated as critical defects from the first day of design, not the last day of testing. If you have ever wondered why a modern airplane's autopilot has 3 completely independent computer systems, each running different code, written by different teams, voting on every decision, the answer traces back, in part, to the Tyler Clinic in 1986. But the deeper lesson is not really about medical devices or airplanes. The deeper lesson is about a kind of confidence that often gets called engineering pragmatism. The engineers who designed the therac 25 were not negligent. They were not lazy, they were not unqualified. They were, by every measure, competent professionals doing serious work. What they did was make a decision that, at the time, felt entirely reasonable. They decided the software was good enough that the hardware safeguards could be removed. They were wrong. And because they were wrong, people died. Software has only gotten more central since then. The systems we now trust with lives are vastly larger and more complex than the therac 25. The same class of bug, a race condition between fast input and slow physical response, ships into production every single day, in less consequential software, written by engineers who have never heard this story. Which raises a question this channel is going to keep asking. How much of our world is now held up by code that nobody has formally verified, written by engineers who trusted themselves a little too much, with no hardware safeguard underneath, in case the software fails? The honest answer, again, is probably more than we think. Voight Cox died in September 1986, about 6 months after his 9th treatment in Tyler. The cancer he had been treated for had not killed him. The treatment had. His name is in the official accident report, so are 5 others. The report runs to 53 pages. Every software engineer working on safety-critical systems is, at some point in their training, given a copy and asked to read it. There are worse ways to be remembered. There are also, almost certain